For centuries, we saw gravity as a mysterious, invisible force. An apple falls from a tree, planets orbit the sun, all held in place by a pull we could calculate, but never truly explain. Then, Albert Einstein offered a revolutionary new vision. He proposed that space and time are not separate and static, but are fused into a single, four-dimensional fabric. Space-time. And this fabric is not flat. It can be bent, stretched, and warped by mass and energy. Imagine space-time as a stretched rubber sheet. A massive object like our sun doesn't pull the Earth. Instead, its immense mass creates a deep curve, a valley in the space-time fabric. The Earth, in its motion, is simply following the straightest possible path through this curved space. What we perceive as the force of gravity is actually the geometry of space-time itself. Our planet is not being pulled. It is rolling along the inside of a cosmic valley created by the sun. One of the most profound predictions of this theory is that gravity can bend light. Just like a planet, a beam of light traveling through space must also follow the curves in the space-time fabric. During a solar eclipse in 1919, astronomers observed starlight bending as it passed the sun, exactly as Einstein predicted. On a grander scale, the immense gravity of entire galaxy clusters can act as a cosmic lens, warping the light from galaxies behind them into beautiful distorted arcs, allowing us to see further back into the universe's history. But the most dramatic proof of curved space-time came a century later, when two massive objects, like black holes or neutron stars, orbit each other and merge. They create violent disturbances, sending ripples across the fabric of space-time. These are gravitational waves. First detected in 2015, these faint tremors travel across the universe at the speed of light, stretching and squeezing everything they pass through. We don't just live in the universe. We live within a dynamic, curving, rippling ocean of space-time that dictates the motion of everything from falling apples to distant galaxies. 0 to 60s, we experience time as a constant, an unstoppable river carrying us from past to future. But Einstein's theory of general relativity revealed a shocking truth. Time is not constant. It is relative. It can be warped, stretched, and slowed by the force of gravity. In the everyday world, this effect is imperceptibly small, but near an object with immense gravity, like a black hole, the consequences are staggering. This isn't science fiction. It is gravitational time dilation. 61 on 20s. Imagine two astronauts embarking on different journeys. The first remains in a stable orbit around Earth, where gravity is familiar. The second ventures out to the most extreme object in the cosmos, a supermassive black hole. As he approaches, the intense gravity of the black hole begins to warp the very fabric of space-time around him. For the astronaut near the black hole, everything feels normal. A minute is still a minute. But for an observer back on Earth, his clock has started to tick at a fraction of the speed of ours, 121 on 80s. As our brave explorer orbits the abyss, time splits into two realities. In his cockpit, he looks out at the universe and sees an accelerated cosmos. Stars and galaxies wheel past in a blur as thousands of years of cosmic history unfold in mere hours of his time. Back on Earth, we would see his ship slow to a near standstill, its image getting redder and fainter as it hovers at the edge of eternity. For him, a coffee break is a few minutes. For us, it could be a lifetime, in 18240s. When the mission is over, the astronaut returns. But he returns to a future he never expected. While he has aged only a few years on his journey, decades have passed for everyone he left behind. His friends, his family, the entire world has moved on. He has traveled not just through space, but through time. This is the ultimate paradox of gravity. The closer you get to its source, the slower your journey through time becomes, making you a visitor in your own future. Every object with mass leaves an imprint on the universe. A gentle curve in the fabric of space-time. A planet creates a small dimple, a star, a deeper well. But what happens when mass is taken to its absolute limit? The story begins with the death of a truly massive star. When it runs out of fuel, gravity wins its final victory. The core collapses under its own weight, crushing matter into a point of infinite density and zero volume. A singularity. This is not just a new object. It is a rupture in reality. This is a black hole. It is the most extreme geometry in the universe. Space-time here is not just curved, it is a bottomless pit. The edge of this pit is the event horizon, a boundary from which nothing, not even light, can escape. It is the point of no return, a place where all paths lead to the center. We see its effect not by what it emits, but by how it consumes, devouring light, bending starlight, and holding a silent, terrifying reign over its domain. Here, time itself breaks. For a distant observer, an object falling into a black hole would appear to slow down, its light stretching into red until it freezes at the event horizon for eternity. But for the object itself, the journey continues. In the moments it takes to cross the horizon, it could theoretically witness thousands, or even millions, of years of cosmic history unfold in the outside universe. It becomes a one-way time traveler, fast-forwarding to the end of time while its own clock ticks on. Inside the event horizon, the laws of physics as we know them cease to exist. Space-time is so warped that the singularity is not a place you can go to, but a future you cannot avoid. The gravitational pull is so different from one end of an object to the other that it is stretched into a stream of atoms, a process aptly named spaghettification. A black hole is more than just a dead star. It is the ultimate proof that mass doesn't just exist in the universe. It dictates the shape of it, and it governs the flow of time itself. At the heart of our Milky Way galaxy, an unseen giant reigns supreme. This is Sagittarius A-Wart, a supermassive black hole, 4 million times more massive than our Sun. It's an object of such immense density that its gravitational pull is inescapable. A cosmic abyss from which not even light can break free. As we venture closer to this enigmatic behemoth, we see how its incredible mass doesn't just pull on nearby stars and gas. It fundamentally warps the very fabric of reality, bending space-time itself into a dizzying vortex. This gravitational well is the engine driving the motion of our entire galaxy, a silent, powerful force shaping the cosmos around it. The influence of Sagittarius A extends beyond simple gravity. Because this black hole is spinning at a tremendous speed, it drags the fabric of space-time along with it, a phenomenon known as frame dragging. Imagine a spinning ball dipped in honey. As the ball rotates, it pulls the honey around it. In the same way, Sagittarius A twists the space-time in its vicinity, creating a swirling cosmic whirlpool. This rapid rotation also distorts the shape of space-time, squashing it from a perfect sphere into an oblong rugby ball-like shape. Anything caught in this current is pulled into a spiraling dance, its fate intertwined with the black hole's relentless spin. This effect is a profound demonstration of Einstein's theory of general relativity, made manifest on a galactic scale. Perhaps the most mind-bending consequence of this extreme gravity is its effect on time. As you approach a black hole, the intense gravitational field causes time to slow down relative to an observer far away. For an object falling toward Sagittarius AA, time stretches to an almost infinite degree. From our distant perspective, it would appear to slow down, dim, and freeze just outside the event horizon, the point of no return. Yet, for the object itself, its journey continues inexorably forward. Due to the extreme distortion of space-time, all possible future paths lead directly to the singularity at the center. In this bizarre reality, moving forward in time is the same as moving toward the black hole's core. The destination is inescapable. The power of Sagittarius A-like isn't just theoretical. Its past fury has left indelible marks on our galaxy. Erupting from its poles are colossal structures known as Fermi bubbles. These are ghost-like remnants of powerful jets of energy that the black hole blasted out millions of years ago, and they now stretch for a staggering 50,000 light-years, towering above and below the galactic plane. More recently, astronomers have detected ripple-like waves in space-time near the black hole, generated by clumps of superheated iron gas orbiting at blistering speeds. These waves are like tremors in the fabric of the universe, carrying information about the chaotic and violent environment just outside the event horizon. Through these observations, we are piecing together the story of our galaxy's central monster. Each discovery, from the warping of space-time to the echoes of ancient eruptions, reveals another layer of its complex character. Sagittarius A is not just a void in space, but a dynamic and influential force that has sculpted the Milky Way over billions of years. By studying this cosmic titan in our own galactic backyard, we unlock secrets about the fundamental laws of physics and the grand, violent evolution of the universe itself.